Right now, inside your hand, trillions of tiny things are moving that no one has ever truly touched. They are electrons, smaller than anything you can picture, and every solid wall, every table, every hand you have ever gripped, you never actually touched at all. We're about to shrink down and chase the strangest thing in the whole universe. An electron that jumps between places with nothing in the middle. A ghost that slips straight through solid walls. A particle that acts like it sits in two spots at once, until the moment you look, and then it picks one. If tiny things that break every rule you thought you knew sound worth your time, tap like and subscribe, and ride with us. The deepest mystery in all of science is hiding inside you right now. Take a breath. We begin. Hold up your hand and look at it. It feels solid. It feels like it ends where the air begins. That feeling is a lie your senses tell you, and the truth is far stranger. Inside every fingertip sit billions of atoms. Inside every atom sit electrons, and the electron is the smallest piece of you that anyone has ever found. It has no known parts. You cannot break it open. It is a full stop at the very bottom of everything. Think about how small an atom already is. If you blew up a single atom until it was as wide as a football stadium, the heavy centre, the nucleus, would be a marble sitting on the 50-yard line. Everything else, all that huge empty space out to the seats, is where the electrons live. And the electron itself would still be too tiny to see. Smaller than a grain of dust in that whole stadium. Now here is the part that stops scientists cold. That marble in the middle, the nucleus, is made of smaller pieces called protons and neutrons. You can split those apart and find even smaller bits inside. But the electron, every time we test it, it comes back with nothing inside. No smaller parts, no width we can measure. It behaves like a single point floating in space, holding a tiny sip of electric charge and almost no weight at all. How light is it? An electron weighs about 2,000 times less than the tiny proton next to it. If the proton were a full backpack loaded for school, the electron would be a single feather resting on top. And yet this feather runs your whole life. Every thought moving through your brain right now is electrons shifting from one cell to the next. Every heartbeat is triggered by tiny sparks of them. The light hitting your eyes as you listen, the sound reaching your ears, the warmth in your skin, all of it is electrons doing their work. You are, in a real way, a machine run by these specks. We have known the electron exists for over 100 years. A scientist named J.J. Thomson found the first hint in 1897, working with a glass tube and a strange glowing beam. He proved the beam was made of tiny charged pieces, way smaller than any atom. People had thought the atom was the smallest thing in the world. Thomson cracked it open and found something smaller hiding inside. Since then, electrons have become the most useful thing humans have ever learned to control. The screen you might be watching, the battery keeping your phone alive, the wires in your walls, every one of them is just us pushing electrons around and telling them where to go so we understand what electrons do. We use them every single second. We have built our entire modern world on top of them. You would think, after a full century, we would know exactly what one is. We do not. The closer scientists look, the weirder the electron gets. It refuses to sit still. It refuses to have a size. It seems to be in many places until you check. And the first shock, the one that breaks your gut feeling about the whole world, is waiting one step away. Because when you press your hand against a table, you never actually touch it. Press your palm flat against the nearest wall right now. You feel it push back. Solid, cold or warm, real. Your whole life has taught you that your skin is meeting the wall. It is not. There is always a gap, a tiny space that nothing crosses. Your hand and the wall never make contact, and they never will. Here is why. The outside of every atom in your skin is covered in electrons. The outside of every atom in the wall is covered in electrons too, and electrons carry a negative electric charge. Two things with the same charge push each other away. Hard. The closer you shove them, the harder they shove back. You have felt this force before without knowing it. Take two magnets and try to press the matching ends together. They fight you. They slide sideways. They refuse to meet. You can feel an invisible cushion between them, springy and stubborn. That is the exact same force that stops your hand from ever reaching the wall. The electrons in your skin and the electrons in the wall are two magnets that will not let each other close. When you knock on a door, your knuckle electrons get near the door electrons and the push spikes up so fast that it slams your hand to a stop. Your brain reads that sudden stop as hard and solid. The knocking sound is that force ringing out. But your knuckle never once landed on the wood. A thin gap held them apart the whole time, way too small to see. Sit in a chair and you are floating, a microscopic hair above the seat, held up on a cushion of pushing electrons. You have been hovering your entire life and never noticed. This means the word touch is a bit of a trick. When you hug someone you love, your electrons and their electrons come very close and push against each other, and your nerves feel that push, and your brain calls it a hug. The warmth is real, the feeling is real, but the two of you never truly meet at the deepest level. A whisper of empty space always stays between every person and everything they hold. Even eating works this way. You bite an apple, and your teeth do not slice through it by touching it. Your teeth force their electron clouds so hard against the apple's electron clouds that the apple's atoms give up and rip apart. You are winning a shoving match, not making contact. Now scale this up. Everything you have ever felt as solid is mostly empty space held firm by these invisible pushes. Remember that stadium with the marble at the center? An atom is that empty, which means a brick wall, a mountain, a planet, they are almost entirely nothing, laced together by electrons refusing to overlap. The solidness of the whole world is a force, not a substance. So the electron builds the feeling of reality itself. Without that push, you would sink through the floor, through the earth endlessly, because there would be nothing solid to stop you. The ground holds you up using electrons alone. That already bends the mind. But it gets stranger because we have quietly assumed one thing this whole time. We have pictured the electron as a tiny ball, a little marble of its own. That picture may be completely wrong. The electron might have no size whatsoever. We keep calling the electron the smallest thing, a tiny ball, a speck. But every serious measurement points to something your brain will fight against. The electron may have no size at all, zero width, a true point in space. Sit with how odd that is. Everything you have ever seen has an edge. A basketball ends, a grain of sand ends, even a speck of dust, way too small for your eye, still has a surface. A place where it stops and the world begins. Your whole life trains you to believe that if a thing exists, it takes up room. The electron seems to break that rule. Scientists have tested it with incredible care, trying to find its width, and they keep coming up empty. As far as anyone can measure, the electron is smaller than the smallest size we can even check. It sits there holding real charge, real magnetism, and yet takes up no space we can find. Picture the challenge like this. Imagine trying to measure the width of a shadow with a ruler. You bring the ruler closer and closer, and the shadow just keeps getting sharper, and you never find its thickness because it may have none. That is where physicists stand with the electron. Every finer tool shows it smaller and it never bottoms out. How small have we checked? Experiments have shown that if the electron has any width, it is at least 10,000 times smaller than a proton, and the proton is already so tiny that trillions would fit on the head of a pin. Push past that and the electron still shows no size. In every equation that works, physicists treat it as a perfect point with nothing spread out around it. This creates a strange problem. The electron carries charge. Charge usually sits on a surface spread over something. But if the electron has no surface, no size, then where does the charge sit? On a point. How can a point hold anything? When scientists try to work this out with older math, the numbers blow up to infinity, which is math screaming that something is missing. They found clever ways to work around the infinity and still make correct predictions. But the honest truth is that a charged thing with no size should not make sense. And yet, there it is. So what is it really? A point cannot spin. A point cannot have parts. A point is barely a thing at all in normal language. And yet this point-like electron has real weight, real charge, and does real work inside you every second. It is as close to nothing as something can get while still being something. Some physicists suspect the electron is not truly a ball or a point in the way we imagine. They think it might be a knot of energy in an invisible field that fills all of space, a little ripple that acts like a particle when we poke it. On that view, asking for its width is like asking how wide a musical note is. The question may not even fit. For now, hold the strangeness. The most important building block of matter, the thing that makes your hand feel solid, might itself take up no room at all. And if you think a sizeless speck is hard to picture, wait until you see how it moves around inside the atom. Because it does not orbit like a planet, no matter what your old science book showed you. Open almost any old science book and you will see the same picture of an atom, a ball in the middle, and little electrons flying around it in neat circles, like planets looping the sun. It is clean. It is simple. It is also wrong. Electrons do not orbit the nucleus. They do not travel in circles. They do not follow a track at all. That famous picture, the one on classroom posters and science logos everywhere, shows something that never actually happens. Here is where the planet idea falls apart. A planet stays in its orbit because gravity pulls it just right, and it keeps a steady, smooth path you could trace with a pencil. If the electron did the same thing, physics says it would have a fatal problem. A charged thing moving in a circle should throw off energy, like water flying off a spinning wheel. It would lose power fast, spiral inward, and crash into the nucleus. The whole atom would collapse in a tiny fraction of a second. Do the math on that and it is brutal. If electrons really orbited like planets, every atom in the universe would have destroyed itself in less time than a blink. You would not exist. Nothing would. The fact that you are here, made of atoms that have lasted billions of years, proves the planet picture cannot be true. So scientists in the early 1900s had a crisis. Atoms clearly held together, electrons clearly stayed away from the centre. But nothing in normal physics explained why. The rules that worked for baseballs and planets simply broke at this size. The answer, when it finally came, threw out the whole idea of a path. An electron in an atom does not go from point to point along a line. It does not have a position the way a car on a road has a position. Instead, it exists as a kind of spread-out haze of chances, thicker in some places and thinner in others, wrapped around the nucleus in strange three-dimensional shapes. Some look like balls, some look like dumbbells, some look like weird clovers and rings that no one would ever guess. Think of it this way. Picture a fast fan blade. When it spins, you stop seeing a single blade and start seeing a blurry disc. You cannot point to where the blade is at any instant, because it is smeared across the whole circle. The electron is stranger than that, because it is not even a blade whipping around fast. It genuinely does not have one spot. It is spread out everywhere in its region, all at once. This spread out haze is where the electron lives, and it explains why atoms survive. There is no spiraling, no crashing, because there is no circling in the first place. The electron settles into a stable cloud, a standing pattern that just holds, like the steady shape a guitar string makes when it hums one note. As long as nothing disturbs it, that pattern lasts forever. This was one of the biggest shocks in all of science. The tidy solar system inside the atom was gone. In its place came something no human eye could ever see, and no simple picture could ever fully capture. To really understand it, we have to look closer at that haze. Because when you ask the simple question, where exactly is the electron right now, the answer is not a place. The answer might be everywhere at once. So the electron does not orbit. It spreads out into a haze around the nucleus. But what is that haze really? It has a name that sounds gentle and hides something wild. Scientists call it the electron cloud. And the truth about this cloud shakes the ground under everything you think is real. The cloud is not made of many electrons. In a hydrogen atom, there is just one electron, and it still forms a full cloud all by itself. So the cloud is not a swarm. It is one electron, somehow smeared across a whole region at once. Every spot in that cloud is a place the single electron might be found. Where the cloud is thick, the electron is very likely to turn up if you check. Where the cloud is thin, it is less likely. Right at the edges, it becomes very unlikely, but never quite zero. The electron is a fog of maybe, thicker here, fainter there, wrapped around the center. Try to hold this. Before anyone looks, the electron does not have a single spot. It is not hiding in one place and keeping it secret from you. As far as the deepest physics can tell, it truly does not have one location. It is genuinely spread through the whole cloud, a mist of chances and nothing more solid than that. Then you check. You fire in some light or run the right test, and in that instant the fog snaps to a single point. The electron shows up at one spot sharp and clear. All the other places it might have been simply vanish. The cloud collapses to a dot the moment you demand an answer. Picture rolling a die inside a closed cup. While it tumbles, it is not showing a number. It is a blur of possibility, all 6 waiting at once. Only when the cup lifts does one number lock in. The electron is stranger, because it is not that it had a hidden number all along. The best evidence says the number did not exist until you looked. The cup lifting is what makes reality choose. This is the heart of quantum physics, and it broke the minds of the smartest people who ever lived. Albert Einstein hated it. He could not accept that the universe worked on chances instead of solid facts. He wrote the famous line that God does not play dice. He spent years trying to prove the electron secretly had a real position all along. He lost. Experiment after experiment showed the fog is real, and the dice are real, and the electron truly has no single home until measured. How thick is this cloud? For a single hydrogen atom, the cloud is only about 100 millionth of an inch wide. So small that 10 million of these atoms in a row would barely stretch across the width of a hair. And inside that impossibly tiny space, one electron manages to be everywhere at once. Now widen the view. Every atom in your body holds these clouds. Every solid thing around you is built from fog. The chair, the floor, your own bones, all of it is made of particles that have no fixed place until something looks. Reality, at its base, is a shimmer of maybe that only turns solid under attention. And if the electron can be spread across a whole cloud, then jumping from one spot to another should be simple. But the way it actually moves inside the atom is the strangest jump in all of nature. It crosses a gap without ever being in the gap. Inside the atom, the electron cloud can take different shapes and sit at different levels. Think of these levels like steps on a ladder. The electron can rest on a low step close to the nucleus, or it can sit on a higher step farther out. Simple enough so far, but how it moves between those steps is one of the eeriest things in all of science. When an electron changes steps, it does not travel between them. It does not slide up the ladder. It does not pass through the space in the middle. One moment it is on the low step, the next moment it is on the high step, and in between it is simply nowhere. It was here, then it was there. It never crossed the gap. Scientists call this a quantum jump, and it is exactly as bizarre as it sounds. Try to imagine it with something you know. Picture a kid on a staircase. In real life, to get from the bottom step to the third step, the kid has to move through the space in between. Their body passes over step 1, step 2, the air between. You could film it and freeze any frame and see them mid-climb. Now imagine the kid blinks from the bottom step to the third step with no frames in between. No moment of being between steps. You could film it forever and never once catch them in the middle, because they were never in the middle. That is a quantum jump. The electron does this every time it changes levels. It vanishes from one energy step and appears on another, and the space between the steps is a place it never occupies. There is no halfway. There is no journey. There is only before and after. Even weirder, the electron cannot stop on the space between steps. On a real ladder you could stand between rungs if you wanted, or hang halfway. The electron cannot. It is only ever allowed on the exact steps, never in between, ever. The in-between energies are forbidden. It is as if the universe only lets the electron exist at certain heights, and erases every value in between. This is where the word quantum comes from. It means a set amount, a chunk. Energy inside the atom comes in chunks, in steps, never in a smooth ramp. The electron can have this much energy or that much, but nothing in between, the same way you can have $1 or $2 in coins, but never $1.50 cents if half cents do not exist. Here is why you should care. Every time an electron jumps down to a lower step, it dumps its extra energy as a tiny flash of light. Every time it jumps up, it swallows a flash of light to pay for the climb. These jumps are the reason anything glows. The colours in a neon sign, the light from the sun, the glow of a fire. All of it is electrons leaping between steps and spitting out light in the process. So this impossible jump, this move through nothing, is happening trillions of times a second all around you, filling your world with light. You are surrounded by tiny leaps that skip over space itself, and a jumping, cloud-shaped, sizeless electron is already almost too much. But we have not even reached its most famous secret. The electron also has something called spin, and the name hides a truth that makes no physical sense at all. Every electron carries something scientists named spin. The name makes you picture a tiny ball whirling around like a top, or a spinning basketball on a fingertip. That picture is wrong, and the real answer is far weirder than a spinning ball. The electron acts in every way like it is spinning. It behaves like a tiny magnet with a north end and a south end, exactly the way a spinning ball of charge would. It responds to magnetic forces the way a spinning charged object should. Every test says, this thing is spinning, but nothing is actually turning. Remember, the electron may have no size at all. It might be a point, and a point cannot spin. There is nothing to rotate. There is no surface to whirl around, no axis to turn on, no parts to move in a circle. Spinning needs a thing with width, and the electron may have none. So it has all the effects of spinning with nothing there to do the spinning. It gets stranger. If the electron really were a little ball whipping around to make this magnetism, scientists worked out how fast its surface would have to move. The answer was faster than the speed of light, and nothing can move faster than light. So the electron simply cannot be a ball spinning fast enough to explain what we see. The spinning ball idea is not just unproven, it is flatly impossible. Yet the magnetism is completely real. It is one of the most precisely measured things in all of science, which we will come back to later. So physicists are stuck with a fact and no simple picture for it. The electron has a property that acts like spin, gives it magnetism, and shapes how atoms behave, but it is a spin with no spinning. They kept the name because it was already stuck, and now every physics student learns to say spin while knowing nothing turns. There is one more twist that breaks your everyday sense completely. Take a normal object and turn it all the way around, a full circle, and it looks exactly the same as when it started. Turn a coin all the way around and it faces the same way. The electron does not work like this. To bring an electron back to its true starting state, you have to turn it around twice. One full turn is not enough. It comes back looking flipped, wrong somehow, and only a second full turn sets it right. Think of how strange that is in normal life. Imagine spinning fully around on your feet, one complete turn, and ending up facing a mirror world, backwards, and needing to spin around a second time to feel normal. Nothing you can hold behaves that way, yet the electron does, and this double turn behavior is measured, real, and used in real machines. This bizarre spin does serious work. It is why some materials are magnetic and others are not. When many electrons line up their spins the same way, their tiny magnetism adds up into a magnet strong enough to hold a note to your fridge. The pull of every magnet you have ever touched comes straight from this spinning that does not spin. So the electron has no size, lives as a cloud, jumps through nothing, and spins without turning. Each fact alone would be strange. Together they should not fit in one thing. And the deepest reason they fit is a secret about what the electron truly is. Sometimes it acts like a solid ball. Sometimes it acts like a spreading wave, and it is somehow both at the very same time. Everything you have ever seen falls into one of two groups. There are things, solid objects you can point at, like a baseball or a rock, and there are waves, spreading ripples that pass through stuff, like sound or the ripples on a pond. A thing is in one place. A wave is spread out. They seem like total opposites, and in your daily life they never mix. The electron is both at once. It is a solid piece you can catch at a single point. It is also a spreading wave that ripples through space, and it is not switching back and forth between the two. It is genuinely both, all the time, until the moment you test it. This sounds impossible because in your world it is. A baseball is a ball, a ripple is a wave. Nothing is ever both. Yet the electron refuses to pick a side, and this double life is one of the deepest truths in all of physics. Here is how each side shows up. When you catch an electron, When you slam it into a screen or trap it in a detector, it always lands as a single point. A tiny dot right there, sharp and clear, exactly like a ball hitting a wall. In that moment, it is fully a particle, a thing with a spot. But while no one is watching it, the electron travels as a wave. It spreads out, it ripples, it flows around corners and through gaps like water spreading through a harbour. It does all the things a wave does, and none of the things a ball does. In that moment, it is fully a wave, spread across space with no single spot. Which one is the real electron? Both. Neither. The question itself may be broken. The electron is a thing our words were never built to describe, because everything we made words for is either a ball or a wave, never both. We are trying to name a creature from a world with different rules using only words from ours. Picture a coin standing on its edge, spinning so fast it is a blur. While it spins, it is neither heads nor tails. It holds both at once, a shimmer of both faces. Only when it falls does it become one or the other. The electron lives in that spinning blur, both natures alive together, until a measurement makes it fall to one. This has a name. Physicists call it wave-particle duality, and it is not a guess or a theory anymore. It has been shown in experiment after experiment for 100 years. Light does it too. So does everything small enough. At the tiny scale, the hard line between things and waves that rules your whole life simply does not exist. How big is this wave nature in real life? For anything you can see, it is far too small to notice. A thrown baseball has a wave, but its wave is so unimaginably tiny that it never matters, which is why balls act like balls. The electron is small enough that its waveside is huge compared to itself, big enough to run the show. That is why the strangeness only shows up down in the world of the very small. This double life is not just a fun fact. It leads straight to the single, most mind-bending experiment ever done. An experiment so strange that the greatest physicist of the century said it holds the only true mystery of the quantum world. You send one electron toward a wall with two doors, and it goes through both. There is one experiment that sits at the centre of all this strangeness. The physicist Richard Feynman, one of the sharpest minds who ever lived, said it holds the only real mystery in the whole quantum world. Everything weird about the electron shows up here. It is called the double-slit experiment, and once you understand it, the world never looks solid again. Set it up in your mind. There is a wall with two narrow doorways cut into it, side by side. We will call them the two slits. Behind that wall is a screen that lights up wherever an electron hits it, like a dot of chalk marking each landing. In front of the wall is a little gun that fires electrons one at a time toward the doors. Start simple. Fire electrons like tiny balls. Common sense says each electron goes through one door or the other, and you should end up with two bright stripes on the screen, one behind each door, like paint sprayed through two gaps. That is what balls would do. That is what your gut expects. That is not what happens. Instead, the screen fills up with many stripes. Bright band, dark band, bright band, dark band, spread across the whole screen. This striped pattern is the fingerprint of waves, not balls. When two sets of ripples cross, they add up in some spots and cancel out in others, making a pattern of strong and weak bands. Water waves do it. Sound does it. And here the electrons are doing it too, even though you fired them like tiny balls. So the electrons are behaving like waves. Fine, we already learned they can. But now comes the part that broke 100 years of physics. Fire the electrons one at a time. Wait between each shot so there is only ever one lonely electron crossing the gap. There is no other electron for it to cross ripples with. Each one goes alone. Surely now you get two simple stripes, since a single electron cannot make a wave pattern by itself. It still makes the striped pattern. Slowly, dot by dot, over thousands of single electrons the bands build up again. Each electron lands as a single dot, like a ball. But the pile of dots forms the wave pattern, band after band. Somehow each lone electron, crossing all by itself, behaves as if it went through both doors at once, and rippled against its own self on the other side. Let that settle. One electron, two doors, and it takes both. Not one or the other, both at the same time, alone. The wave that spreads out from that single electron passes through both slits, overlaps itself on the far side, and that overlap decides where the single dot is likely to land. A thing with no part split its path in two and interfered with itself. Picture one person walking toward two open doorways and, without splitting into two people, still managing to walk through both and meet themselves coming out. That is the electron every single time. This is confirmed. It has been done countless times, with electrons and with bigger particles too. It is one of the most solid facts in science, and it is also one of the least understood. Nobody fully knows how a single particle goes through two doors at once. But the mystery has one more level, and it is the level that made Einstein lose sleep. Because if you try to peek and catch the electron going through, everything changes. Stay with that lonely electron a moment longer, because what it does deserves a closer look. It changes what a wave even means. When you drop two stones into a still pond, each one sends out rings. Where two rings meet, something happens. In some spots the water piles higher, because both waves push up together. In other spots the water goes flat, because one wave pushes up while the other pulls down, and they cancel. This crossing and cancelling has a name. Scientists call it interference. It is the clearest sign in the world that you're dealing with waves and not with balls. Two stones make two sets of rings. That is normal. But in the double-slit experiment, there is only one electron in the whole setup at a time. There is no second stone. There is no partner to make a second set of rings. And yet the interference pattern appears anyway, band after band, as if two waves crossed. The only explanation is staggering. The single electron's own wave spreads out, passes through both doors, and comes out the far side as two overlapping ripples that then cross each other. The electron interferes with itself. It is the stone, and it is also the second stone. One particle, splitting its own wave, crossing its own path, cancelling and adding against its own self. This is the deepest proof that the electron is truly a wave while it travels, spread across real space, wide enough to cover both doors at once. A ball could never do this. A ball goes through one door, full stop. Only something spread out, something wave-like, can pass through two openings and then meet itself. Think about how big that makes a single electron in a sense. To go through both doors, its wave has to be at least as wide as the gap between them. So for that instant, one electron is not a tiny dot at all. It is spread out across a space many times wider than the doors themselves, wide enough to be at both openings together. The electron that lands as a pinpoint was, moments before, a wave stretched across the whole setup. Here is a way to feel it. Imagine you're standing at the mouth of two tunnels trying to get to the other side. As a normal person, you pick one tunnel and walk through it. As an electron, you flow into both tunnels at once, come out the far ends as two spreading versions of yourself, and those two versions ripple through each other before settling into the single you that steps out. You are genuinely in both tunnels. The math does not work any other way, and this is measured. The bright and dark bands appear exactly where the wave math predicts they should, down to fine detail. Scientists can calculate where the peaks and gaps will fall, and the electrons land in perfect agreement, thousands of times over. The self-interference of a single particle is one of the best confirmed facts in all of physics. So the electron travels as a spread-out wave, wide and rippling, taking every path at once. That is settled. But now comes the twist that turned this from strange into deeply unsettling. Scientists wanted to catch the electron in the act. They set up a tiny detector at the doors to see which one it really used. The moment they looked, the electron stopped playing both doors, and that changed everything we thought we knew about reality. Scientists could not stand the mystery. A single electron going through both doors at once? They had to catch it in the act. So they placed a tiny detector right at the slits, a little watcher that would notice which door each electron actually used. The plan was simple: peek and finally see the electron split itself in two. The electron refused. The instant they switched on the watcher, the electron stopped going through both doors. It picked one, just one. Each electron now sailed through a single door like an ordinary ball, and the striped wave pattern on the screen vanished. In its place came two plain stripes, exactly what balls would make. The strangeness switched off the moment someone looked. Read that again, because it is one of the most disturbing facts humans have ever found. The electron behaves one way when unwatched, and a completely different way when watched. Looking at it changes what it does. Not looking at it lets it stay a spread-out wave through both doors. Looking forces it to become a single ball through one. The act of watching reshapes reality. Turn the watcher off, and the wave pattern comes right back. Turn it on, and the pattern dies again. Scientists have flipped this switch back and forth countless times, and the electron responds every time, like it somehow knows whether it is being observed. Watched, it acts like a particle. Unwatched, it acts like a wave. The choice seems to depend on whether anyone is checking. This drove Einstein to the edge. He could not accept a universe where looking at something changes it. He believed the electron had a real solid path all along, going through one true door, and that our watching just revealed a fact that was already there. He spent his later years trying to prove it. He argued. He designed clever traps. He tried to show the strangeness was a trick of incomplete knowledge. He lost. Experiment after experiment, with better and better tools, kept showing the same thing. The electron truly does not choose a door until it is measured. There is no hidden path waiting to be uncovered. Before the look, both doors are alive. After the look, only one. The watching does not reveal reality. It seems to create it. Try to hold what this means. A rock in the dark, a coin in a closed box, we assume they have definite states whether or not we look. The moon is up there whether or not anyone sees it. That assumption is your bedrock sense of reality. Down at the electron scale, that bedrock cracks. The electron does not seem to have a settled reality until something forces it to. Its features hang in a fog of maybe until a measurement snaps them into fact. And no, this is not about human eyes or minds being magic. The watcher is just a machine. What matters is that measuring the electron, poking it hard enough to learn where it is, disturbs it and forces it to choose. Any interaction that pulls out real information does it. The universe seems to hold reality open until the question is asked. To this day, nobody fully agrees on what this means. It is confirmed 1,000 times over and still deeply mysterious. The strangeness is real. The reason for it is not settled. But an electron that can be a spread-out wave can do something even more impossible than passing through two doors. It can pass straight through a solid wall, roll a ball at a hill. If you roll it slowly, it climbs partway up and rolls back down. It does not have enough push to get over. This is the most obvious thing in the world. To get past a barrier, you need enough energy to reach the top. Not enough energy, and you never make it to the other side, ever. The electron breaks this rule. Send an electron at a barrier it does not have enough energy to cross, a wall it simply cannot climb, and sometimes it appears on the other side anyway. It did not go over the top, it did not smash through. It was on this side, and then it was on that side. Having crossed a barrier it never had the energy to beat. Scientists call this quantum tunneling. Here is how something so impossible can happen. Remember that the electron is a spread-out wave of maybe, not a solid ball in one spot. When that wave of maybe hits a barrier, most of it bounces back, but a thin sliver of the wave leaks into the wall, and if the wall is thin enough, pokes out the far side. And where the wave pokes out, there is a small chance the electron will simply turn up there. So now and then, an electron placed on one side of a barrier is later found on the other side, having crossed a wall it could never climb. Think of it like this. Imagine you're throwing a ball against a solid brick wall in your yard over and over. Every time it bounces back. That is normal life. Now imagine that every so often, once in a great while, the ball just quietly appears in your neighbour's yard on the far side of the wall, without breaking it, without going over it. The wall is still whole. The ball is simply on the other side now. For an electron, that is not a fantasy. It happens constantly. The trick only works because the electron is so small and so spread out. The thinner the wall, the better the chance the electron slips through. Make the wall a little thicker, and the odds of tunnelling drop fast. Make it thick enough, and the electron never crosses, just like the ball at the hill. So tunnelling only shows up across tiny gaps, walls just a few atoms wide. But at that scale, it happens all the time, in countless places right now. This is confirmed beyond any doubt. It is measured in labs every day. And far from being a lab curiosity, tunnelling runs some of the most important machines and processes in the universe. It is a real force shaping real things, from the gadget in your pocket to the star that lights your sky. Sit with how strange this is next to everything you know. Your whole life, walls have meant no. A locked door means you cannot pass. A barrier means stop. That certainty is built into how you move through the world, and down at the electron scale, that certainty dissolves. A wall is no longer a hard no. It becomes a maybe, a chance. Sometimes the answer to a solid barrier is simply, the electron is on the other side now and no one can say exactly how. An electron slipping through walls sounds like a magic trick with no purpose. But this trick may be the single reason the sun shines and the sky stays lit. Without it, the stars themselves would go dark. Look up at the sun, that blazing ball that lights your days and warms your skin. Every bit of its power comes from deep in its core, where it fuses tiny bits of matter together and releases enormous energy. And here is the shock. The sun should not be able to do this. By the plain rules of physics, the sun is not hot enough to shine. It only works because of the wall walking trick you just learned. Here is the problem the sun faces. To make its energy, the sun has to smash the cores of hydrogen atoms together until they stick and fuse. But those cores all carry positive charge, and same charges push each other away. Hard, just like matching magnet ends. The closer two cores get, the more fiercely they shove apart. To force them together, you need to ram them at incredible speed, which means incredible heat. Scientists measured the sun's core temperature. It is around 27 million degrees Fahrenheit. Unthinkably hot. And yet, when they did the math, that heat is still not enough. The cores in the sun are not moving fast enough to beat the push and slam together. By the strict rules, they should bounce off each other every time, and the sun should never fuse anything, and the sky should be dark and cold. You should not be here, yet the sun shines. So what fills the gap? Quantum tunneling. The cores do not have enough energy to climb over the wall of repulsion between them. But because they are tiny quantum things, spread out as waves of maybe, they do not need to climb over. Sometimes their waves leak through the barrier, and they simply appear close enough to fuse, having tunneled through a wall they could never beat. The sun runs on particles cheating past a barrier that should stop them cold. Think about the scale of that. Every ray of sunlight that has ever touched your face, every plant that ever grew, every warm day you've ever felt, all of it traces back to this quantum trick happening trillions upon trillions of times, each second in the sun's heart. Without tunneling, the barrier would win, and no star in the sky would ever have lit. The universe would be a cold, dark place with no sunlight and no life. And it is not just our sun. Every star you see at night runs on the same trick. All those distant points of light are giant furnaces powered by particles tunneling through walls they should not be able to cross. Look up at the night sky, and you are seeing quantum weirdness written across the whole universe. Each star a monument to particles breaking the obvious rules. Even stranger, this makes the sun a slow, steady burner instead of a quick explosion. Because tunneling is a game of chance, only a small fraction of cores get through the barrier at any moment. So the sun sips its fuel gently over billions of years instead of blowing up all at once. That slow pace is why the sun has burned steadily long enough for life to appear and grow on Earth. The same quantum chanciness that lets particles cross walls also sets the calm, patient rhythm that made you possible. So the strangest behaviour of the electron and its cousins is not a useless oddity. It lights the sky and warms the world. And that same wall-walking trick is also buried inside the phone or device you might be holding right now. That same wall-walking trick, the one lighting up the sun, is sitting in your pocket right now. Quantum tunneling is not only a thing for stars far away, it is built into the phones, laptops, and memory chips that run your daily life. The strangest behaviour of the electron has been quietly put to work by human hands. Start with the memory in your phone that saves your photos and messages even when the power is off. That kind of memory is called flash memory, and it works by trapping electrons in tiny sealed pockets. When electrons are stuffed into a pocket, that spot counts as a 1. When the pocket is empty, it counts as a 0. Strings of these ones and zeros are how the chip stores every picture, song, and text you own. Simple enough, but here is the trick. To get the electrons into those sealed pockets in the first place, the chip has to push them through a thin barrier, a little wall meant to keep them locked in. The electrons do not have the energy to cross that wall the normal way, so the chip uses tunneling. It sets things up so the electrons slip straight through the barrier and land in the pocket, then the barrier holds them there. Every photo you have ever saved was stored by making electrons walk through walls on purpose. Think about how many times that happens. A single memory chip holds billions of these tiny pockets. Every time you snap a picture, countless electrons tunnel through barriers to lock that image in place. The trick that powers the sun is happening billions of times inside your hand every time you hit save. Tunneling shows up in another huge way too, and this one is a problem engineers fight every day. As companies pack more and more parts into chips, the tiny walls between those parts get thinner and thinner. And you already know what happens when a wall for electrons gets too thin. They tunnel through it. So on modern chips, electrons start leaking across barriers where they are not supposed to go, slipping through walls that were meant to stop them. This leak wastes power and can cause errors. Engineers now have to design around a quantum effect just to keep our devices working. This is one of the biggest walls, in a different sense, that computer makers have slammed into. For decades they made chips faster by making the parts smaller and smaller. But now the parts are getting so tiny, only a handful of atoms across, that tunneling leaks are becoming a serious barrier. The strange behaviour of the electron is pushing back against how small our machines can get. A quantum trick is setting a limit on the future of computers. There is even a special microscope that uses tunneling on purpose to see single atoms. It brings a sharp tip very close to a surface, so close that electrons tunnel across the tiny gap between them. By measuring that tunneling as the tip moves, scientists can map out a surface atom by atom and make pictures of individual atoms sitting in rows. The first time humans ever saw single atoms clearly, they did it by reading electrons that walked through a gap. So the electron's wildest trick runs your gadgets, lights the stars, and lets us see the atom itself. Yet for all this power, electrons also follow a strict and hidden rule, a law that decides why you do not fall through your own chair. Electrons follow a strict law that shapes the entire world. It sounds boring at first, and then you realize it is the reason matter can exist at all. The rule is this: in any single atom, no two electrons are allowed to be in the exact same state. They cannot match completely. Each one must be at least a little different from all the others. Scientists call it the Pauli exclusion principle, after Wolfgang Pauli, who figured it out. Break down what a state means here. An electron in an atom has a set of features: which energy step it sits on, what shape its cloud takes, which way its spin points. Together these make its state like a full address for the electron inside the atom. The rule says no two electrons in the same atom can share the exact same address. If one electron already has a certain address, every other electron in that atom is banned from it and must go somewhere else. This forces electrons to stack up in layers. The first electrons fill the lowest, closest addresses. Once those are full, new electrons are forbidden from crowding in, so they must sit at higher levels, farther out. Add more electrons and they are pushed out further still, filling shell after shell around the nucleus. The electrons are stacked into layers only because they are banned from sharing. This stacking is the secret behind the whole world of chemistry. The way an atom's outermost electrons are arranged decides how it links up with other atoms, which decides what kind of material it forms. Whether something is a metal, a gas, water, or bone comes down to how its electrons stack under this rule. The entire chart of elements, every different kind of atom there is, gets its order from this one law about electrons refusing to match. Picture a giant stadium where every seat has a unique number, and the rule is that no two people can share a seat. People fill the front rows first, the best seats closest to the field. Once those fill up, latecomers are forced into higher and higher rows because the good seats are taken and sharing is banned. The crowd stacks upward, filling the stadium level by level, only because two people cannot occupy one seat. Electrons fill an atom the very same way, forced outward by a ban on sharing. Why do electrons obey this? It ties back to that strange double turn spin from earlier. Particles like the electron, the ones with that half-turn kind of spin, are built by the deep rules of nature so they can never share a state. It is woven into what they are. Nobody chose it. The universe simply comes with this law stitched in, and every electron everywhere follows it without fail. And the reach of this rule is staggering. It does not just organize single atoms, it stretches across all matter. Because electrons refuse to share states, they refuse to be crushed into the same space. Pack them together and they push back hard, purely because they are banned from matching. This resistance is a force in its own right, and it holds up things far bigger than atoms. In fact, this ban on sharing is the reason you do not sink through your chair, the reason the ground is solid under your feet, and the reason whole dead stars can stay standing when they should collapse. One quiet rule about electrons not matching holds up your body and the corpses of stars alike. Sit down and feel the chair press back against you. You already learned that your atoms never truly touch the chair's atoms, that electrons pushing apart keep a tiny gap between you and everything you lean on. But there is a second, deeper reason you do not sink through the seat, and it comes straight from that ban on electrons sharing a state. Here is the puzzle. Atoms are almost entirely empty space, remember, like a marble in a whole stadium. So when you sit down, why do all that empty space in your atoms and all that empty space in the chair not just pass through each other? Two mostly empty things should be able to overlap easily, the way two clouds drift through one another. Yet they do not. The chair stays solid. You stay on top. Why? Part of the answer is the electric push between electrons, the same charge shoving apart. But there is more. As you press down, you try to force your electrons and the chair's electrons into the same small space, into the same states, and the Pauli rule flatly forbids it. Electrons cannot share a state, so when you try to squeeze them together they resist with a force that has nothing to do with electric charge. They push back simply because nature will not let them match. This resistance is often called degeneracy pressure, and it is fierce. So the solidness of your chair comes from two things working together. The electric push between like charges, and this deeper refusal of electrons to be crammed into the same states. Together they make a barrier so strong that your body rests on top of the seat, held up by rules about tiny particles you will never see. Think about what that means for the whole solid world. Every solid object, the floor, a table, a mountain, a car, is held together and kept firm by electrons refusing to share and refusing to overlap. Take away this rule and matter would collapse, atoms would fall into each other, everything solid would crush down into something unimaginably dense. The entire firmness of the world, the very fact that things have shape and hold their form, rests on this one quiet law. Picture trying to push two crowded buses together, packed so full that every single seat is taken and people are standing in every inch. To merge the buses, you would have to force two people into the same spot, and there is simply no room. So the buses jam and refuse to combine. Now imagine that no matter how hard you push, the rule that two people cannot share a spot never bends. The buses would never merge, held apart by pure lack of room. Solid matter works like that, packed with electrons that cannot double up, refusing to be pushed into one another. This is not a small effect. The force from electrons refusing to share is powerful enough to hold up your entire body against gravity, all day, without you ever thinking about it. Every moment you stand, sit, or lie down, you are being held up by a law about electron states working silently in every atom you're made of. And if this force can hold up your body, imagine how strong it must be to hold up something far heavier. Because this exact same electron stubbornness is the only thing keeping certain dead stars from crushing themselves into oblivion. Whole burned-out suns are held up by nothing more than electrons that refuse to share. Far out in space, there are dead stars that should have collapsed into nothing, and the only thing holding them up is the stubbornness of electrons. The same rule that keeps you from sinking through your chair keeps entire burned-out suns from crushing themselves out of existence. It is one of the most amazing places this tiny law reaches. Here is what happens when a star like our sun runs out of fuel. For billions of years, a star shines by fusing atoms in its core, and that outward blast of energy pushes back against the star's own crushing gravity, keeping it puffed up and steady. But when the fuel runs low, the outward push fades. Now gravity has nothing to fight it, and the star begins to collapse, falling inward under its own enormous weight. Nothing seems able to stop it. Something does stop it. As the star crushes down, its electrons get packed tighter and tighter, forced closer together than ever. And you know the rule. Electrons cannot share the same state. As gravity tries to jam them into the same tiny spaces, They push back with that fierce refusal, that degeneracy pressure, and this push is so strong that it halts the collapse of an entire star. Gravity, one of the great forces of the universe, gets stopped cold by electrons refusing to match. The result is a white dwarf, a dead star core about the size of the whole Earth, but holding as much stuff as the Sun. Cram that much matter into that smaller ball, and it becomes almost unbelievably dense. A single spoonful of white dwarf material would weigh about as much as a fully loaded truck, and this crushingly heavy ball is held up, kept from collapsing further, by nothing but the stubbornness of electrons that will not share a state. A rule you can trace to a lab on Earth is holding up a star. Our own Sun will end this way. Billions of years from now, it will run out of fuel, swell up, shed its outer layers, and leave behind a white dwarf. A dead ember held firm by electron pressure, slowly cooling in the dark. The same law that holds you in your chair right now will one day hold up the corpse of our Sun. But there is a limit to how much even electrons can bear. A scientist named Subrahmanyan Chandrasekhar worked out the breaking point as a young man on a long boat trip doing the math by hand. He found that if a dead star holds more than about 1.5 times the mass of our Sun, gravity finally wins. The electrons cannot push hard enough, and the star keeps collapsing past the white dwarf stage into something even denser and stranger. This breaking point is now named after him. Think about what that means. The stubbornness of electrons is strong, but it is not endless. Below the limit, electrons win and you get a white dwarf. Above it, gravity crushes through, and the star falls further, sometimes into an even denser object, sometimes exploding in a blast that outshines a whole galaxy. The fate of a dying star hangs on a contest between gravity and a rule about tiny particles. So the electron holds up your chair and holds up dead stars, using the same quiet law. And this humble particle has one more claim to fame. Its magnetism is the most perfectly measured thing humans have ever tested, matching theory to a precision that will leave you stunned. The electron holds a record that might be the most impressive in all of science. Its magnetism has been measured and predicted so precisely that the match between them is the most accurate agreement between human theory and reality ever achieved. Nothing else humans have ever tested comes close, and this record belongs to the humble electron. Remember that the electron acts like a tiny magnet because of its strange spin. Every electron has a certain strength to this magnetism, a specific number that says how strong its little magnet is. Scientists wanted to know this number exactly, so they did two things. They measured it in careful experiments, and they calculated it from the deep theory of how electrons work. Then they checked whether the measured number and the predicted number matched. They matched to an almost unbelievable degree. The measured value and the predicted value agree to more than 10 decimal places. 10 places past the point, digit after digit, all lining up perfectly. To give you a feel for that kind of precision, imagine measuring the distance across the entire United States, from New York to Los Angeles, and getting it right to within the width of a single human hair. That is roughly how precise this agreement is. Human theory predicted the electron's magnetism that exactly, and reality matched. Sit with how astonishing that is. Scientists wrote down equations based on their understanding of the electron, cranked through the math, and produced a number. Then they went into the lab, measured the real electron, and got the same number, matching digit after digit past the decimal point. The universe agreed with the human calculation to a precision finer than almost anything you can picture. It is one of the greatest triumphs in the history of thinking. This incredible match is a huge deal, because it tells us our deepest theory of the electron is right. The theory that predicts this number is called quantum electrodynamics, the theory of how electrons and light interact. The fact that it nails the electron's magnetism so perfectly means this theory is one of the most tested and most correct ideas humans have ever come up with. Every time the match holds, it confirms that we truly do understand something profound about how the electron behaves, and getting that predicted number was brutally hard. To calculate the electron's magnetism this precisely, physicists had to account for the electron constantly interacting with a storm of invisible activity around it. Empty space near an electron is not truly empty. It fizzes with fleeting particles popping in and out, and all of that subtly tugs on the electron's magnetism. To get the prediction right, scientists had to add up thousands of tiny contributions from all this hidden fizz, and when they did, it matched reality perfectly. The invisible storm around the electron is real, and we can prove it to 10 decimal places, so the electron gives us both a deep mystery and our single most precise piece of knowledge. We do not know what the electron truly is, yet we can predict its magnetism more exactly than we can predict almost anything else in the universe. Understanding and mystery sitting side by side in one tiny particle. For all this precision, the electron still holds surprises about the plainest things, like how it moves through a simple wire. Because when electricity flows, the electrons themselves crawl slower than you would ever guess. Flip a light switch and the room lights up instantly. It feels like electrons must be racing through the wire at tremendous speed to make that happen so fast. Here is a fact that will surprise you. Inside that wire, the electrons themselves are crawling. They move slower than an ant walking across the floor. Slower than a snail. And yet the light comes on the instant you flip the switch. How can both be true? Start with how slow the electrons really move. When current flows through a normal wire, the individual electrons drift along at a truly tiny pace. In a typical wire carrying normal household current, an electron creeps forward at less than a 50th of an inch per second. At that rate, a single electron might take over an hour to travel the length of a short lamp cord. You could easily outrun it. A tired ant would beat it in a race. This slow crawl even has a name. Scientists call it the drift speed, so the electrons themselves are barely moving. That seems to make no sense next to how fast electricity works. Flip a switch and the bulb lights up with no delay you could ever notice. If the electrons are crawling slower than an ant, how does the light turn on instantly? There has to be something else going on, and there is. Here is the secret. The wire is already packed full of electrons everywhere along its length before you even flip the switch. They are sitting there, jammed together throughout the whole wire like water already filling a long hose. When you flip the switch, you do not wait for electrons to travel from the switch all the way to the bulb. Instead, you give a push at one end, and that push travels through the whole crowd of electrons almost instantly, nudging the ones at the far end to move right away. Picture a long tube stuffed completely full of marbles end to end with no gaps. Push one more marble in at your end, and a marble pops out the far end at almost the same instant. The marble that pops out is not the one you pushed. It was already sitting there at the far end. Your push simply travelled through the whole line of marbles almost immediately, even though each marble barely moved. Electricity works just like that. The push races through, while each electron shuffles forward only a hair. So two things are true at once. The electrons crawl, slower than an ant, and the push, the signal that tells them to move, races along at nearly the speed of light. When you flip the switch, the signal to start moving reaches the bulb in a tiny fraction of a second, and every electron along the wire, including the ones already at the bulb, starts drifting at once. The bulb lights instantly because the electrons there were ready and waiting, needing only the signal to go. This split between the slow crawl of the electrons and the lightning speed of the signal is one of the neat surprises hiding in something as ordinary as a wire. The stuff that carries the message barely moves, while the message itself flies. Every time you turn on a light, you are using this trick without knowing it. That racing signal, moving at nearly the speed of light, deserves a closer look, because the gap between how slow the electrons go and how fast the message travels is even wider and stranger than it first appears. The electrons crawl slower than an ant, yet the signal that moves them races at nearly the speed of light. This gap between the two speeds is one of the widest and strangest in all of nature. Let us really look at how fast that signal goes and why it matters for your entire life. When you flip a switch, the push that tells the electrons to move travels down the wire as an electric signal. That signal moves at a huge fraction of the speed of light, often more than half of it. Light itself travels fast enough to circle the whole Earth about 7 times in a single second. The signal in your wires moves at a big chunk of that speed. So while each electron barely shuffles forward, the command to shuffle flies down the wire almost as fast as anything in the universe can go. Think about how enormous that difference is. The electrons drift at less than an inch per second. The signal moves at over 300 million miles per hour. That is a gap of unthinkable size between the thing that moves and the message that moves it. It is as if a stadium full of people barely shifted in their seats, yet a wave passed through the entire crowd in the blink of an eye. The crawl and the race live in the same wire at the same time. This racing signal runs your whole connected world. Every time you send a text, load a video or tap a button, electric signals are flying through wires and circuits at nearly light speed to make it happen. The reason your actions feel instant, the reason a message can cross a city in a heartbeat, is that these signals travel so incredibly fast. The modern world runs on the speed of this push, not on the crawl of the electrons themselves. But here is a limit that even this blazing speed runs into, and it shapes technology in a way you might not expect. Nothing can travel faster than light, including these signals. And even though light speed feels instant to us, it is not truly instant. Over long distances, that tiny travel time adds up. A signal sent across the world, or up to a satellite and back, takes a small but real amount of time to arrive, simply because even light speed has a limit. This is why, on a video call with someone far away, you sometimes notice a tiny delay before they respond. Part of that delay is the signal physically travelling the long distance at light speed, which still takes a measurable moment across thousands of miles. The speed of the push is fixed by the universe, and not even our best technology can beat it. The electron signal is fast, but the cosmos sets a hard ceiling that nothing can cross. Engineers who build fast computers fight this limit too. In a computer that does billions of steps each second, even the tiny time it takes a signal to cross the chip starts to matter. The parts have to be placed close together so the signals do not waste precious moments travelling. The speed of the electron's push, huge as it is, becomes a real barrier when you're trying to compute fast enough. The universe's speed limit reaches right into the machines on our desks, so the electron gives us a crawl and a race in the same breath, and even the race has a ceiling set by light. Yet for all these surprises, the deepest strangeness may be this. Every single electron in the entire universe is exactly, perfectly identical to every other one. Here is a fact so strange that it hides in plain sight. Every single electron in the entire universe is exactly identical to every other electron. Not similar, not nearly the same, perfectly precisely the same in every way that can be measured. And this perfect sameness is one of the deepest and weirdest truths about our world. Think about how odd that is compared to everything else you know. No two snowflakes are exactly alike. No two grains of sand match perfectly. No two people, no two leaves, no two anything in your daily life are truly identical. Everything you have ever seen has tiny differences, little flaws and quirks that make each one unique. That is just how the world seems to work. Every object is a little different from every other. Electrons shatter that expectation completely. Take any electron from your fingertip and any electron from a star billions of miles away, and they are exactly the same. Same weight, down to the last digit. Same charge, exactly. Same spin, same everything. There is no scratch, no dent, no serial number, no tiny flaw that tells one electron apart from another. Swap two electrons and there is genuinely no difference at all. The universe stamps out every electron from the same perfect mold, with zero variation, everywhere, always. This perfect sameness is not just a nice coincidence, it is essential, and it shapes how the whole world works. Remember the rule that no two electrons in an atom can share a state, the one that stacks electrons in layers and gives us all of chemistry. That rule only makes sense because electrons are truly identical. If electrons had little differences, the deep laws that build atoms and matter would fall apart. The sameness of electrons is woven into the foundation of everything solid. Picture a factory that stamps out coins. Even the best real factory makes coins with tiny differences, a little more metal here, a scratch there. No two exactly alike under a strong enough microscope. Now imagine a factory so perfect that every single coin it makes is exactly identical, atom for atom, with no difference whatsoever, no matter how closely you look. That is beyond anything humans can build. Yet the universe does exactly this with electrons, producing endless copies that are flawlessly the same, across all of space and all of time. Scientists have tested this sameness in clever ways, and it holds up perfectly. In fact, the strange behavior of identical particles has real, measurable effects. When two truly identical electrons get close and interact, they behave in ways that would be impossible if they had even the tiniest difference between them. Experiments confirm again and again that electrons are perfectly interchangeable, with no hidden features that set them apart. The sameness is real, tested, and rock solid. This raises a question that sounds almost silly until you think hard about it. Why should every electron be exactly the same? What forces the universe to make endless perfect copies with never a single one out of line? Nobody fully knows. It is simply how reality is built. The cosmos, for reasons we do not understand, comes with a rule that all electrons must be identical, forever, everywhere. And this deep mystery once sparked one of the wildest ideas any scientist ever dared to think. If every electron is exactly the same, one famous physicist wondered, then maybe there is a stunning reason why. Maybe every electron in the universe is secretly the very same single electron. One day, a physicist had an idea so wild it sounds like a dream, and yet it came from serious science. The idea was this. Maybe every electron in the universe is exactly the same because they are all, somehow, the very same single electron appearing in countless places at once. One electron being everything, everywhere, all at the same time. The story goes that the great physicist John Wheeler called up his student one day, a young man named Richard Feynman, buzzing with excitement. Wheeler said he knew why all electrons are identical. It is because there is only one electron in the whole universe. That single electron zips around through space and time, weaving back and forth, and every place its path crosses the present moment, we see an electron. Since it is all the same one, of course every electron looks perfectly identical. They are one and the same particle, caught over and over. Try to picture how this could work. Imagine a single thread being woven back and forth through a piece of cloth. If you only look at one thin slice of the cloth, you see many separate threads crossing it, and they all look the same because they are all the same thread. Wheeler's idea was that the one electron weaves through time like that thread, and the moment we live in is that thin slice. Every crossing looks like a separate electron, but they are all the same, one thread stitched through the fabric of time. The idea gets even stranger when you ask how the electron weaves backward. To make this work, the single electron would have to travel forward in time, then turn around and travel backward in time, then forward again, over and over, threading through all of history. And here is the beautiful twist. When an electron travels backward in time, the math shows it would look exactly like antimatter, like the electron's opposite twin, which you will meet very soon. So Wheeler's idea neatly explained why antimatter exists too. It is just the one electron, moving backward on part of its journey. Now, is this idea actually true? Almost certainly not, and even Feynman quickly spotted a problem. If every electron were the same one weaving through time, then the number of electrons moving forward and the number moving backward should be about equal. That would mean the universe has about as much antimatter as regular matter. But when we look around, the universe is full of regular matter and has very little antimatter. The books do not balance. So the one electron idea, as stated, cannot be the full story. Even so, this wild idea left a lasting mark on science. The insight that an electron moving backward in time looks like its antimatter twin turned out to be deeply useful. Feynman took that piece and built it into his own groundbreaking work on how particles behave, work that later helped win him the highest prize in physics. A dreamlike idea that was probably wrong still handed science a tool that was profoundly right, and that is often how the strangest ideas work. Even when they miss, they can crack open a door to something true. The one electron dream failed as a full answer, but it pointed straight at one of the most mind-bending real things in the universe. The electron truly does have an opposite twin, a mirror version made of antimatter, and when the two ever meet, they destroy each other completely. The electron has an opposite twin, a mirror version of itself, and this twin is made of antimatter. It sounds like something from a comic book, and yet it is completely real, confirmed in labs and even used in hospitals. The electron's twin is called the positron, and it is one of the strangest and most real things in all of science. Here is what the twin is like. The positron matches the electron in almost every way. Same tiny weight exactly. Same size or lack of size. Same kind of spin. In nearly every feature, the positron is a perfect copy of the electron, but there is one crucial flip. The electron carries a negative electric charge, and the positron carries a positive one. It is the same particle turned inside out on charge, a mirror image where the charge is reversed. The electron and the positron are twins with opposite signs. This is what antimatter means. For many kinds of matter particles, there is an antiversion, a twin with the opposite charge. The positron is the antimatter twin of the electron, the first piece of antimatter ever discovered, and antimatter is not just a wild theory. Scientists make positrons in labs, study them closely, and even put them to work in real machines that help people every day. In fact, you may have benefited from antimatter without knowing it. Hospitals use a scanning machine called a PET scanner to look inside the body and find disease. The letters PET stand for positron emission tomography, and the whole thing runs on positrons, on antimatter. Doctors use the electron's evil twin to make detailed pictures inside living people and catch problems like cancer early. The mirror version of the electron is saving lives in hospitals right now. But antimatter comes with a dramatic and dangerous rule, and it is the reason antimatter is so famous. When a piece of matter meets its antimatter twin, the two destroy each other completely. If an electron meets a positron, both particles vanish in an instant, wiped out entirely, and their mass turns into a flash of pure energy. Nothing is left behind but light. The twins cannot coexist. Bring them together and they annihilate, gone in a burst. Think about how total that is. Normally, when things collide, they bounce, break, or stick. Matter usually stays matter. But when matter meets antimatter, both simply cease to exist as particles, converting entirely into energy. It is the most complete destruction possible in physics. Nothing else turns matter so fully and so instantly into pure energy. The electron and its twin cannot share the same space and survive. Picture two drops of water, one made of something that unmakes the other on contact. Touch them together and both drops vanish in a flash of light, leaving nothing behind. That never happens with real water, of course, but with an electron and a positron, it happens every time they meet. Two real particles, gone in an instant, their entire substance turned to light. This raises a haunting question that scientists still wrestle with. If matter and antimatter destroy each other, and the early universe should have made them in equal amounts, why is the universe full of matter today with almost no antimatter left? Something tipped the balance in favour of matter, and we are made of the leftovers. Nobody fully knows why. Before we chase that mystery further, there is something worth pausing on. The flash of light when the twins meet is not random. It is a perfect trade. Matter turned exactly into energy, following the most famous equation in all of science. When an electron meets its antimatter twin, both vanish in a flash of pure light. This moment of total destruction is worth slowing down on because it reveals one of the deepest truths in all of physics. It shows that matter and energy are two forms of the same thing, and that one can turn fully into the other. Watch what happens in that instant. The electron and the positron come together. In less than a blink, both particles are gone. Where two solid bits of matter existed, now there is only light, two flashes of energy speeding away. The particles did not break into smaller pieces. They did not scatter. Their entire being, all their mass, converted completely into energy. Matter became light, fully and instantly. This is the clearest proof of the most famous idea in science, the one Albert Einstein gave us. Mass and energy are the same thing in different forms, and you can turn one into the other. His famous short equation says exactly this, that a small amount of mass holds a huge amount of energy locked inside. When an electron and positron annihilate, that locked away energy is released all at once as light. The equation is not just a formula on a chalkboard. It comes true every time these twins meet, and the trade goes both ways, which is even more astonishing. Just as matter can turn into energy, energy can turn into matter. If you gather enough energy in one tiny spot, you can create an electron and a positron out of that pure energy, making matter appear where there was none. Scientists do this in labs. They concentrate energy and watch particles pop into existence. Matter can be born from energy, and energy can be born from matter. They are two sides of one coin. Think about what this means for the world around you. The The solid stuff you're made of, your bones, your blood, every atom in your body, is in a deep sense a form of frozen energy. All that mass could, in principle, be converted back into a staggering amount of energy. You're walking around as a lump of concentrated energy in solid form. The line between the solid you and pure energy is thinner than it ever seemed. Picture ice and steam. They look completely different, one hard and solid, one a wispy gas. Yet they are the same water, just in different forms, and you can turn one into the other with heat or cold. Matter and energy are like that, two forms of one deeper thing. The electron is like the ice, solid and definite. The flash of light it becomes is like the steam spread out and free, and nature can turn one into the other, back and forth. This deep link between matter and energy powers some of the biggest things in the universe. It is why the sun and stars can pour out so much energy, turning a bit of their mass into the light that crosses space to reach us. It is behind the most powerful energy sources humans have ever tapped. The simple idea proven by two vanishing twins scales all the way up to the engines of stars. Remarkably, the existence of this antimatter twin was not first found by accident in a lab. It was predicted ahead of time by a quiet man staring at an equation who trusted the math even when it seemed to be saying something impossible. He essentially discovered antimatter with a pencil, years before anyone saw it. Antimatter was discovered with a pencil before anyone ever saw it. A quiet, brilliant scientist named Paul Dirac worked out that the electron must have an opposite twin, using nothing but math, years before any experiment found one. It is one of the most stunning examples in history of the human mind reaching truth through pure thought. Here is what happened. In the late 1920s, Dirac was trying to write an equation that fully described how the electron behaves, one that fit together the strange new quantum rules and Einstein's rules about speed and energy. He was a man of very few words, famous for his long silences and his deep focus on math. He worked and worked until he found an equation that beautifully captured the electron. It was a triumph, one of the great equations in all of physics. But his equation had a puzzle buried inside it. The math did not just describe the ordinary electron, it also allowed for another particle, one just like the electron but with the opposite charge, a positive twin. At first this seemed like a mistake, a strange extra answer that surely meant nothing. In everyday math, equations sometimes give extra answers you throw away, like a negative number for something that cannot be negative. Many would have ignored it. Dirac did not ignore it. He trusted his equation. He took the math seriously and made a bold claim. If the equation says there is a twin particle with opposite charge, then maybe that particle really exists, out there in the world waiting to be found. He predicted a brand new kind of matter, based purely on believing what the math told him, even though no one had ever seen such a thing. It was an act of extraordinary courage in thinking. For a few years, his prediction hung in the air, unproven and doubted. Then, in 1932, a scientist named Carl Anderson was studying particles that rained down from space using a special detector. In his data, he spotted a track left by a particle that looked exactly like an electron but curved the wrong way, the way a positive charge would. He had found the positron, the electron's antimatter twin, exactly as Dirac's equation had foretold. The pencil prediction had come true. Think about how remarkable that is. Dirac sat with an equation, saw a hint of something no human had ever observed, trusted the math over common sense, and predicted a whole new form of matter. Years later, nature proved him right. He found antimatter in the language of math before anyone found it in the real world. It stands as one of the greatest triumphs of pure reasoning in the history of science, and it won him the highest prize in physics. This tells us something profound about the universe. The deep math that describes reality is not just a tool for bookkeeping, it seems to know things. When the equations pointed to a hidden twin, that twin was really there. Again and again in physics, the math has predicted things no one expected, and the universe has turned out to obey. It is as if reality is written in a mathematical language that we are slowly learning to read. The electron keeps rewarding this kind of deep attention. It hides its secrets, then reveals them to those who look closely enough. And one of its most everyday secrets is also one of its most beautiful. The electron is the reason anything sticks together at all. It is the glue that holds you and everything in one piece. The electron is the glue that holds you together. Every part of your body, every object around you, stays in one piece because of electrons linking atoms to each other. Without electrons doing this job, you would fall apart into a cloud of loose atoms in an instant. The electron is the reason anything solid can even exist as a whole. Here is how the gluing works. Atoms join together to make everything from water to bone to steel. And the thing that joins them is their electrons. When two atoms come close, they can share or trade their outer electrons, and that sharing creates a link between them, holding them together. Scientists call this link a chemical bond. Every bond that holds any two atoms together is made by electrons. They are the hooks and ties that build all of matter. Think about what that means for your own body. You are made of a huge number of atoms, and they are all connected into molecules, into cells, into tissues, into you. Every one of those connections, every bond holding your atoms in their proper places, is made by electrons. The shape of your body, the structure of your muscles, the strands that carry your genes, all of it is held together by electrons linking atom to atom. You are quite literally glued together by these tiny particles, and it is not just you. Everything solid or liquid around you holds its form because of electron bonds. Water is water because electrons bond hydrogen and oxygen atoms in a certain way. Wood, plastic, metal, glass, stone, all of them are collections of atoms bound by shared electrons. Change the way the electrons bond, and you change the material entirely. The whole variety of stuff in the world comes from the different ways electrons can link atoms together. Picture a huge structure built from tiny building blocks, where every block is connected to its neighbours by tiny hooks. If all the hooks vanished, the whole structure would instantly crumble into a heap of loose blocks. Electrons are those hooks for all of matter. They reach between atoms and hold them fast, keeping the vast structure of the world from falling into dust. Remove the electron bonds and everything solid would collapse into scattered atoms in less than a heartbeat. This gluing power also explains why chemical reactions release or absorb energy, which runs so much of your life. When electrons rearrange their bonds, breaking old links and forming new ones, energy is released or taken in. This is what happens when fuel burns, when food powers your body, when a battery pushes out electricity. All of it comes down to electrons shifting their bonds and moving energy around. The electron does not just hold matter together, it also drives the energy that keeps living things alive. Even the strength of materials comes from electrons. Why is steel strong and chalk weak? Because of how tightly and in what pattern the electrons bond the atoms inside them. Strong bonds make strong materials. Weaker bonds make things that crumble easily. Engineers who design everything from bridges to phones are really working with electron bonds, choosing materials whose electrons hold together in just the right way. So the electron builds and holds the entire physical world, including you. And it does one more everyday miracle that you experience constantly without ever thinking about it. Every colour you have ever seen, every shade of everything, is the work of electrons releasing light. Every colour you have ever seen is made by electrons. The red of an apple, the blue of the sky, the green of grass, every shade of everything you have ever looked at comes from electrons releasing or absorbing light. Colour, one of the richest parts of your experience, is entirely the work of these tiny particles. Once you understand this, you can never look at the world the same way. Here is how electrons make colour. Remember the energy steps inside an atom and how electrons jump between them. When an electron jumps down from a higher step to a lower one, it releases a flash of light. And here is the key. The size of the jump decides the colour of that light. A big jump makes light of one colour, a smaller jump makes light of another. Every colour of light matches a certain size of electron jump, so the colours you see are electrons taking jumps of different sizes and giving off light to match. It works the other way too. When light hits an object, the electrons in that object can absorb certain colours, swallowing the light to jump up a step while letting other colours bounce off. The colours that bounce off are the ones you see. So when you look at a red apple, its electrons are swallowing most colours of light and reflecting red back to your eyes. The apple looks red because of which jumps its electrons can make. Every object's colour is a fingerprint of how its electrons handle light. Think about how much of your world this covers. Every painting, every sunset, every colourful thing that has ever caught your eye is electrons at work, absorbing some colours and releasing others. The entire visual richness of your life, all the beauty of colour, is built from electron jumps. You live inside a world painted entirely by these particles leaping between energy steps. This even lets scientists read the stars. When light from a distant star is spread out into its colours, certain colours are missing, swallowed by the electrons in the star's atoms. Each kind of atom absorbs its own special set of colours, like a barcode. So by looking at which colours are missing from a star's light, scientists can tell exactly what that star is made of, even though it is trillions of miles away. Electrons let us know the ingredients of stars we will never visit just by reading the colours in their light. Picture a piano where each key plays a different note. The size of an electron's jump is like which key gets pressed, and the colour of light it releases is like the note you hear. Small jumps and big jumps make different colours, the way different keys make different notes. Every atom is like a piano that can only play certain notes, certain colours, based on the jumps its electrons are allowed to make. The whole universe of colour is this cosmic music, played by electrons on the keys of energy steps. So the next time you see a bright colour, you are watching electrons in action, jumping and releasing light in a pattern that your eye reads as that shade. The beauty of colour is the electron made visible. It is one of the few places where you can almost see the quantum world directly, painted across everything you look at. And one of the most beautiful colour shows in all of nature comes from electrons crashing into the sky itself, painting the night with glowing curtains of light. Some of the most beautiful lights in the whole world are made by electrons crashing into the sky. Near the far north and far south of our planet, glowing curtains of green and pink and purple ripple across the night sky in one of nature's greatest shows. These are the northern and southern lights, and they are painted entirely by electrons slamming into the air high above. Here is where these electrons come from. Our sun does not just send out light, it also blasts out a constant stream of tiny particles, including huge numbers of electrons, flowing out into space in every direction. This stream is called the solar wind, and some of it heads straight for Earth. So our planet is constantly being showered by electrons and other particles thrown off by the sun, racing across space toward us. Now, Earth has a shield, and this is where it gets beautiful. Our planet is wrapped in a magnetic field, an invisible force that surrounds the whole Earth like a protective bubble. When the sun's electrons reach us, this magnetic field grabs them and steers most of them away, protecting us. But near the north and south poles, the magnetic field funnels some of those electrons down into our atmosphere. There, high above the ground, the electrons crash into the air. When those electrons slam into the atoms in our upper air, they give those atoms a jolt of energy, kicking their electrons up to higher steps. And you already know what happens next. When those electrons jump back down, they release light. The colour of that light depends on which kind of atom got hit and how big the jump was. Oxygen high up glows green and sometimes red. Nitrogen glows blue and purple. So the whole rippling curtain of colour is countless electrons jumping down steps and releasing light all across the sky. Think about the scale of this. The glowing lights can stretch across hundreds of miles of sky, shimmering and dancing as the stream of particles shifts. Those waves of light are the direct result of electrons from the sun, 93 million miles away, crossing all that space, getting funneled by Earth's magnetic shield and crashing into our air to paint the sky. You are watching a battle between the sun and Earth's magnetic field, written in glowing colour across the night. Picture a giant glowing sign, where electricity flowing through the gas inside makes it light up with colour. The northern lights work in a similar way, except the electricity is a stream of electrons from the sun, and the gas is our own atmosphere, and the sign is the entire sky. Nature runs the biggest glowing display imaginable, powered by electrons pouring in from space and striking the air we breathe. This light show is also a sign of the invisible shield that protects all life on Earth. That same magnetic field steering the electrons into beautiful lights is also blocking most of the sun's dangerous particle stream from reaching the ground. Without it, that constant blast of particles could strip away our air over time and harm living things. So the northern lights are a visible reminder of an invisible protection, drawn across the sky by the very electrons being turned away. Beauty and safety, painted together by tiny particles. For all the drama electrons cause, from painting skies to lighting stars, they hide a quiet mystery too. As far as anyone can tell, an electron never ages, never breaks down, and never dies. The electron may be immortal. As far as anyone can tell, an electron never ages, never wears out, and never falls apart. It has no known end. In a universe where everything else eventually breaks down, decays, or dies, the electron seems to simply go on forever. It is one of the quietest and most staggering facts about this tiny particle. Think about how strange that is. Everything in your world runs down over time. People age, metal rusts, mountains slowly wear away. Even many other tiny particles are unstable, meaning they break apart into smaller pieces after a while. Physicists have measured the lifespans of many particles, and lots of them fall apart in tiny fractions of a second. Decay is the normal fate of things, big and small. Almost nothing lasts forever. The electron seems to be an exception. Scientists have looked very hard for any sign that electrons break down or decay over time, and they have found none. Every test says the electron is stable, holding together with no end in sight. They have even worked out that if the electron does decay, its lifespan must be unimaginably long, far, far longer than the entire age of the universe so far. In fact, the measured lower limit on an electron's life is so huge that, for all practical purposes, the electron is immortal. Why is the electron so stable? There is a beautiful reason rooted in deep physics. For a particle to decay, it has to break apart into lighter particles. But the electron is the lightest particle that carries electric charge. There is nothing lighter for it to break into that would still keep the charge accounted for. And nature has a strict rule that electric charge can never just disappear. So the electron is trapped in its stability. It cannot decay, because there is nothing lighter for it to become without breaking one of the universe's deepest laws. Its immortality is protected by the rules of reality itself. Think about what this means for the electrons inside you. The electrons in your body are ancient, almost beyond imagining. Many of them were made in the first moments after the birth of the universe, nearly 14 billion years ago. They have existed since almost the beginning of time, drifting through space, joining stars, forming planets, and eventually becoming part of you. The electrons in your fingertip are some of the oldest things in existence, and they will keep on existing long after you're gone. Picture a candle flame that never burns down, glowing on and on without ever using up its wax. Everything you know is like a normal candle, slowly consuming itself, heading toward an end. The electron is like that impossible flame that simply never goes out. While stars are born and die, while galaxies form and drift apart, the humble electron keeps going, unchanged, ageless, quietly outlasting everything grand around it. This gives the electron a strange kind of permanence in a changing universe. Nearly everything else is temporary. Even protons, the particles in the atom's core, might possibly decay someday over spans of time too vast to picture. But the electron, small and simple, may truly be forever. It is one of the very few things in all of reality that seems to have no expiration date at all. An immortal particle is remarkable enough. But the electron has one more secret that even Einstein called spooky, a connection between two electrons so strange he refused to believe it was real. Yet it is real, and it may change the future. Two electrons can be linked in a way so strange that Einstein himself called it spooky, and refused to believe it. Yet it is completely real, proven in labs around the world. When two electrons share this link, doing something to one seems to instantly affect the other, even if they are far apart. Scientists call this link entanglement, and it is one of the deepest mysteries in all of physics. Here is what the link means. You can prepare two electrons together in a special way so their properties become tied to each other. Remember the strange electron spin, which can point in different directions and stays a fog of maybe until measured. When two electrons are entangled, their spins are locked together. Whatever one turns out to be, the other must be the matching opposite. They are bound by an invisible connection, sharing one linked fate. Now comes the spooky part. Separate the two entangled electrons. Send one far away, across the room, across a city, in principle, across the galaxy. They stay linked. Then measure the spin of one electron. In that instant, it snaps out of its fog and takes a definite value. And the moment it does, the other electron, no matter how far away, instantly takes the matching opposite value. It settles into its answer at the same moment, as if it somehow knew what happened to its partner far away. This drove Einstein up the wall. It seemed to suggest that the two electrons were talking to each other instantly across any distance, faster than light, which his rules said was impossible. He called it spooky action at a distance and insisted it could not be the true picture. He believed the electrons must have secretly carried their answers all along, like two gloves packed in separate boxes, where opening one box just reveals which glove was always inside. He was sure there was no real spooky link, only hidden information decided in advance. He was wrong, and this time scientists proved it with careful experiments. A physicist named John Bell found a clever way to test whether the electrons carried secret answers all along, or whether the spooky link was real. Experiment after experiment gave the same answer. The electrons do not carry hidden answers decided in advance. The link is genuinely real. Measuring one truly does affect the other instantly, in a way that has no everyday explanation. The universe really is spooky, exactly as Einstein feared. Picture two magic coins that are linked. You separate them, sending one to a friend across the world, and both are spinning as a blur of maybe. Neither heads nor tails yet. The instant you look at yours and see heads, your friend's coin, at that same moment becomes tails, guaranteed, no matter the distance. No real coins do this, but entangled electrons do exactly this, and it has been shown over and over. There is one careful catch that keeps this from breaking the speed of light. You cannot use this link to send a message faster than light, because you cannot control which answer your electron gives. You only find out the connection worked after comparing results. So the deep rules of the universe still hold, even with this spooky link woven through them. Reality is strange, but it is strange in a careful, consistent way. This spooky link is not just a curiosity. Scientists are now learning to control single electrons and their strange links to build powerful new machines, and to do that, they first had to catch a single electron and hold it still, alone, for a very long time. Scientists have managed to trap a single electron all by itself and hold it in place for months at a time. Think about how astonishing that is. The electron is one of the tiniest things in existence, spread out as a fog of maybe, slipping through walls, refusing to sit still, and yet clever scientists have caught just one, held it alone, and studied it for a long, long time. It is one of the great achievements of careful experiment. Here is why this is so hard. An electron is unimaginably small and light, and it never stops moving. It cannot be held with tweezers or placed in a tiny box because any normal container is made of atoms whose own electrons would just push it around or swallow it up. To hold a single electron, scientists needed a completely different kind of trap, one made not of walls but of invisible forces. They built cages out of electric and magnetic fields, shaped to gently corner one electron and keep it hovering in place. These special traps can hold a single electron suspended in a tiny space, floating there, held by fields alone. Scientists cool everything down to nearly the coldest temperature possible, so the electron barely jitters, and then they can keep watch on it. In some experiments, they have kept the same single electron trapped for months on end, studying it the whole time. One lonely electron held still and watched day after day. It is like catching a single specific raindrop in a storm and keeping it in one place for a whole season. Why go to all this trouble? Because a single trapped electron lets scientists measure its properties with breathtaking precision. Remember the record-breaking measurement of the electron's magnetism, the most precise agreement in all of science? That kind of measurement was done using trapped single electrons. By isolating just one away from all the noise of other particles, scientists can study it so carefully that they nail down its features to more decimal places than almost anything else known. The lonely electron reveals its secrets only when it is truly alone. Trapping single electrons also opened the door to a whole new kind of technology. Once you can catch and control one electron at a time, you can start using its strange quantum properties on purpose. You can set its spin, link it to other electrons, and use those tricks to store and process information in brand new ways. This is one of the foundations of quantum computers, machines that could one day solve problems far beyond what any normal computer can handle. Learning to hold single electrons is a first step toward a whole new age of technology. Picture trying to catch a single, specific molecule of air in a room and hold it perfectly still in the center, without touching it, using only invisible forces for months. It sounds impossible. Yet with electrons, scientists have done something even harder and made it work. The skill and cleverness this takes is a testament to how far human ingenuity can reach, all the way down to holding one of the smallest things there is. So we have gone from never being able to see an electron to catching one and studying it alone for months. And that growing control over single electrons leads to one of the strangest and most powerful electron behaviors of all. Under the right conditions, electrons can pair up and flow forever, with absolutely no resistance, in a state that seems to defy the ordinary rules entirely. Under the right conditions, electrons can pair up and flow forever, with zero resistance, in a state so strange it seems to break the normal rules of electricity. A current that once starts never stops, running on and on without losing any energy, potentially for billions of years. This almost magical behavior is called superconductivity, and it is one of the most remarkable things electrons can do. Start with how normal electricity works. In an ordinary wire, when electrons flow, they bump into the atoms of the wire and get jostled around, losing a little energy as they go. This lost energy turns into heat, and it is why wires warm up, and why some electricity is always wasted. This bumping and energy loss is called resistance, and it exists in every normal wire. It is the reason no ordinary current can flow forever. Bit by bit, resistance eats it away. Now here is the strange part. When certain materials are cooled down to extremely cold temperatures, something amazing happens. Their resistance drops all the way to zero. The electrons stop bumping and losing energy entirely. They pair up in a special way and glide through the material without any friction at all. A current flowing in such a material just keeps going, around and around, never fading, never stopping. Scientists have started currents in superconducting loops and watched them run for years without any measurable loss. In principle, such a current could flow for longer than the age of the universe. Think about how odd this is. In your everyday world, everything that moves eventually slows down and stops because of friction. Roll a ball and it stops. Push a cart and it slows. Nothing keeps moving forever on its own. Superconducting electrons break that expectation completely. They flow with no friction, no slowing, no stopping. It is as close to perpetual motion as nature allows, and it happens because of the strange way electrons behave when they team up in the cold. How do the electrons pull this off? Normally electrons push each other apart since they share the same charge. But in a superconductor under the right freezing conditions, they find a way to gently pair up and move together in perfect step, like dancers moving as one. This teamwork lets them slip through the material without bumping into anything, avoiding all the jostling that causes resistance. The pairing is a deeply quantum trick, one that only shows up when everything is cold enough and calm enough for the electrons to cooperate. This zero resistance flow is already doing incredible things. Superconductors can carry huge currents and make extremely powerful magnets. These magnets are used in hospital scanning machines that take detailed pictures inside the body. They are used in machines that smash particles together to study the universe's deepest secrets. They could one day carry electricity across whole countries with no waste at all, or power trains that float above their tracks and glide with almost no friction. The strange flow of paired electrons could reshape how we live. Picture a crowd of people trying to cross a packed room. Normally they bump and jostle and slow each other down, but imagine them suddenly moving in perfect unison, gliding through the room as one smooth wave, never colliding, never slowing. That is what superconducting electrons do, and it lets them flow forever. The catch, for now, is the deep cold required, which is why scientists are racing to find materials that can do this closer to normal temperatures. Even with all these wonders, from forever flow to spooky links to immortality, the electron guards one final secret. After more than a century of study, no one truly knows what an electron actually is. after more than a century of studying the electron, using it, and building our entire world on it, here is the humbling truth. No one truly knows what an electron actually is. We have measured it more precisely than almost anything else in existence. We have learned to trap it, link it, and put it to work in 1,000 ways. And still, at the deepest level, the electron remains a profound mystery. This is where our journey ends, standing before something we command yet do not understand. Look back at everything we have seen. The electron has no size that we can find, behaving like a point with no width at all. It exists as a spread-out fog of maybe, with no definite place until we look. It jumps between energy steps without crossing the space between. It spins without anything actually spinning. It is a wave and a particle at the same time. It walks through solid walls. It has an immortal life, a spooky link to distant partners, and an evil antimatter twin. Every single one of these is confirmed, real, and tested, and not one of them fits the way our everyday world works. So what is it, at bottom? What is the real nature of this thing? Here we run into the edge of human knowledge. Physicists have a beautiful and successful picture that describes the electron as a ripple in an invisible field that fills all of space, a kind of vibration in the fabric of reality. This picture predicts the electron's behavior with stunning accuracy. But even this deep picture does not really tell us what the electron is in the way you might want. It tells us how the electron acts and how to predict what it will do, without ever fully lifting the veil on its true nature. Think about the strange place this leaves us. We have built our whole modern civilization on the electron. Every screen, every computer, every light, every phone runs on our control of these particles. We shape them, guide them, and rely on them every second of every day. And yet the thing itself, the electron at its core, remains as mysterious as ever. We are like people who have learned to play a magnificent instrument perfectly without ever understanding what music truly is. Our skill is total. Our understanding is not. Maybe that is the deepest lesson the electron has to teach. The universe, at its foundation, is stranger than our minds were built to grasp. Our everyday sense of solid objects, of definite places, of things that either are or are not, simply breaks down at this tiny scale. The electron obeys a different, deeper set of rules, ones we can write in math and test in labs, but ones we cannot fully picture in our heads. It is a messenger from a layer of reality that does not play by our expectations. And here is the wonder in that. The greatest mystery in all of science is not far away in some distant galaxy. It is right here, inside your own hand, in every atom of your body, in everything you touch and see. You are made of these mysteries. You are built from trillions of tiny riddles that no one has fully solved. The strangest thing in the universe is not out there in the dark between the stars. It is woven into you, right now, humming quietly inside every part of what you are. So the next time you touch something and feel it as solid, remember, you're never quite touching it. And the thing doing the pushing, the thing building your whole reality, is a particle we have chased for 100 years and still cannot name. The electron keeps its secret, and that secret is hiding inside every atom you touch.